Hi, this is multivariable 14.3. We got local linearity and the differential. Those are the two things that we're going to be doing. So in regular calculus, what we did was we did local linearization in the xy plane. So all we did was take the equation of the line where the slope was found from the derivative. And then we went ahead and brought this term over to the other side, and so we get f of x is approximated by some initial value plus the change, and the change is determined by the slope and then whatever our x value is there. So now we're going to be moving into two variables, and so we have the equation of a plane that we did before. So we have some initial value, slope in the x direction, slope in the y direction, and then that was the equation that we did get for a plane. So if we want to do a tangent plane, all we have to do is take that same equation and put it into the form here now with the differential. So this is the differential of x, x minus a, and this is the differential of y, y minus b. So some initial plus the change in the x direction plus the change in the y direction. That would give us a tangent plane equation. And then we also can move on to the tangent plane approximation and even extend it to more variables if you wish. So now if I take this, f of xy can be approximated by f of ab, I had to write that in there, plus the change in the x direction, change in the y direction. That would give us an approximation at some point ab. So in and around that area, that little plane is going to approximate a curve. And so we have this picture right here. So if we have a curve, and this is some surface that we do have, if we have this and then we do a tangent to a point, here's my point right here, and then this would be the tangent plane that I'm looking at from that. Okay, so that would be an approximation of the curve in and around this area. So when we're adding a dimension, it's not a tangent line approximation anymore, it's a tangent plane approximation. Nice. And that's the shape that we do get that's produced from this tangent situation that we do have now. And so when we zoom in to see local linearity, this is the curve that we do have, and we're going to zoom in once and then twice. What happens as we keep on zooming in? Well, it's going to look flatter and flatter and flatter, so it's going to look like a plane. And then if we have a contour diagram, what we can do is we can go ahead and zoom in here and see what happens to our contour lines as we zoom in. And as you notice, zooming in, the contour lines get more and more regular. It's kind of like if you're sitting on the hillside right here, and this is a big mountain or something like that. Now you just look in your regular little area that you're in, you have some kind of elevation problems. And then if you look at where your foot is standing, well, it's going to be probably pretty regular where your foot is being placed. And so that's kind of the idea behind that contour diagram when we zoom in. So we zoom in and the lines will be a lot more regular as we do that. So let's look at some examples. Example number 1 says that we want to find the tangent plane of this function right here at the point 109. So what we're going to do is go ahead and find the differential for x, differential for y, and put this all together. So let's take the differential for x of xy, and then if we take that, the e to the y goes away, and so then it's just going to be 1 plus 2x. And if I take my differential with respect to y, treat y as a variable, it's going to be e to the y. Okay, so that's all we have for our 2. And then if I plug in, I need f of 1, 0. That's going to give me the value of 1, 0, plugging in 1, that would be 1 plus 1, that would be 8. So then I need my differentials at the point 1, 0, so I just will plug that in. So if I got 8 plus my differential, plugging in a and b, plugging in 1, 0 into here, that would just give me a 3. And then that would be my x minus my a value, which is my 1 from right here. And then I'm going to go ahead and add in the differential for y evaluated at AB, which is this one here, plug in 1, 0, and I'm going to get a 1. So that's going to be 1 times y minus my 0. And I made a small mistake here. F of 1, 0 is 9, not 8. So I don't know if I can erase this. Yeah, I can. Good. So then this would be a 9 right there. And so this is 9. And then if you simplify this, I believe we get 6 plus 3x. And then I got plus y. Okay, so that is the tangent plane to this function when we zero in on this point right here, 1, 0, 9. Then example 2 just works off of this previous example 1, and it just says use this approximation to evaluate the point, and we want to estimate what is the value of the curve at this point. Well, we could actually plug it in here, which we'll do to find the actual, but then we also plug it into here to find the estimate. So go ahead and do that. Now I set this up wrong. I don't need the z-value because I'm going to estimate the z-value, so let's see what happens. So if I plug into the actual, I'm going to get 9.5314. If I do the approximation through my plane that I did, I get 9.5. Not bad. Well, relative to what error we want to look at. Okay, they have table of values and they have other things too, but just remember that if we can't find the differentials, we're going to go ahead and use the approximation using AROC. So if you did have a table of values, or maybe if you had a contour map of different things and you can't find the exact differential, go ahead and use AROC as an approximation for our, well, our pieces right here and right here. You might have to do average rate of change. Okay, the differential, that's the other part of this lesson. And when we look at the differential, what is the differential? Well, it's, when we talk about it, it's infinitesimally small value of the variable. So we've used dx, we've used dy, and now we're going to use dz or df. Okay, so this is not a partial, but this is just a representation of that small piece. So if we take our tangent line approximation, which we did have already, I'm losing that f there someplace. So I'm going to take this piece and bring it over here. So this is going to be f of xy minus f of ab. And then that's going to be equal to f partial with respect to x, ab, x minus a, and then the y one. So now this piece right here is just a change in f. So that's going to be my delta f. Now if we go over here, we have x minus a. Well, that could be some sort of x naught or whatever, but that is going to be my change in x. And then here, this one would be my change in y. Those will all turn into differentials when we look at this more specifically. So we can simplify it a little bit into this, and then turn it into our differential notation as we get really small f. This would be approximately equal to, or should we say equal to, f, the partial with respect to x of ab, and then that would be dx plus the partial with respect to y, and then that would be dy. That's the one that we want. So in order to find this, when they ask for this, the partial for the function, I'm sorry, the df, what you have to do then is just find this partial, put a dx, find this partial, put a dy, and that's it. So the differential, we've used it quite a bit because it's been the integrand plus the dx as part of the integral that we've used before. But this is how we represent this with our df, and you also could call it dz. And shortcut, they don't put in the a and b, and they just write it like this. So here's the small piece of our graph again, and then what that is that's going to give us this plane. Patchwork that puts together this whole thing here, and that's just one piece of it. And so the plane is the graph of df. So we have our dy, we have our dx, and put it together. That little piece of the plane is going to be our df that we're looking at. So let's do example number 3. What we have to do is we said we had to find the partial with respect to x, and we had to find the partial with respect to y. So then this is for x. Oh, this is a funky one. We're going to use a product rule. So x times the derivative of the second. So first times the derivative of the second. So I'm going to take and get the negative sign of my 2xy, leave that alone, and then I need to chain off the derivative of the inside. With respect to x, that's going to be a 2y, holding y constant and x as my variable. Now with my y being the variable, x constant, oh, I forgot to finish this off, sorry, plus the second times the derivative of the first, so then that would just be cosine of 2xy. And then if I look at this one doesn't have a product rule because the x is considered a constant. So it's just going to go along for the ride. Derivative of the cosine is negative sign. And I'm going to leave the inside alone. And then chain off the derivative of the inside. The derivative of the inside, if I have y as the variable, is going to be just times 2x. So then my df is going to be equal to this piece right here. So that's my partial for x, and then cover that up, and then put a dx. And then I take my partial for y, and then I go ahead and cover that one up, and then I top it off for the differential piece. So that's it. So that's write the differential for this function right here. Now example 4 says do the same thing, except for I want to do it at a point. So if I plug in this 2 comma pi over 4, I'm going to get negative 2, so I'm just plugging it into here. Negative 2 times pi over 4, which just turns out to be pi, or negative pi. So inside the negative 2, the 2xy just becomes pi, but the sine of pi, 0. And then we get just cosine of pi, which would be a negative 1. And then if I do the same thing for the y, plugging in the 2 for my x, and then the pi over 4 for my y, this one's just going to turn out to be 0. So if I want to write the partial derivative for this at this point, that would just be then df, just that thing right there, is going to be equal to negative 1 dx plus 0 dy. So you don't even need that. Okay, so that's all that we got for differentials. So I don't think this is too bad. In fact, I find it kind of fun. It puts us back into doing more straightforward calculus work than some of the other things, but I hope you're having fun with it. Take care. Have a great day.